tell us about trading T-gates for dirty qubits in state preparation and unitary synthesis.
All right, thank you for the introduction. This is work that's done with Vadim from Microsoft and also Luke from MIT, while I was an intern there. So we want to look at the problem of preparing quantum states on the quantum computer and also compiling unitaries, arbitrary unitaries in terms of primitive gates on the quantum computer. These are very important subroutines that you find in quite a lot of quantum algorithms. However, they are very expensive. The most expensive gates that we usually encounter in the fault tolerance setting are the T-gates. And in this talk, I'll talk about how we can reduce the T cost of these subroutines by some interesting factor. By using more dirty qubits, I'll talk more about what dirty qubits are shortly. So more broadly, we want to solve what is called in the field the data input problem. A lot of quantum algorithms that we find interesting have this structure. We have some classical data, maybe it describes your chemistry molecule, maybe in nitrogen or carbon capture or material science, or maybe this classical data is your training vectors in machine learning. In this, common setting, we want to feed this classical data into a quantum computer, do some kind of processing, and then get an output of a computation that solves our problem. However, it turns out that this is actually quite difficult for a lot of problems because there's a key bottleneck, which is how you actually load your data into a quantum computer. So there are actually quite a few different settings for this kind of process flow. In some cases, people study quantum data in and quantum data out, but that is out of scope here, and those approaches come with their own pros and cons. Here we focus on classical in and classical out. And in this situation, loading data is difficult. So how difficult? Well, here are some examples. When we look at, say, the case of Hamiltonian simulation, this is where you have a Hamiltonian with some number of n terms on, say, q qubits. And we want to come up with a quantum circuit that approximates time evolution by this Hamiltonian. So you'd have, say, n Pauli terms, each with some coefficients. And now the cost of this would be proportional to the time of simulation. And this proportionality is constant is multiplied by the number of queries, the cost of your queries. And it happens that if your n coefficients are completely arbitrary, rather than some very uniform thing like a uniform superposition, then every query costs n gates, one gate, or 1 gates for each term. And there are situations where in this cost per query of these n gates, that is dominated by the cost of loading your classical data in. In a typical problem, the number of terms that we have is polynomial in the number of qubits. For instance, in chemistry, it's n to the 4. So if you can, say, load data faster than n to the 4 time, that's great because that directly affects how fast you can simulate your Hamiltonian. Another common example application is in machine learning. Here, instead of having n terms in your Hamiltonian, you have n training vectors of dimension n, m. These training vectors live on log m qubits, and it has been common to claim exponential speedups in the case where the number of training vectors is exponential in the number of qubits. However, this complexity, this is expressed in terms of queries to the routine that loads your classical data, and this can be very expensive. One way to handwave this away is to assume less standard models of computation where you have access to a QRAM oracle. And in principle, QRAM has a depth that is logarithmic in the number of terms, so that's exponential. But if you were to actually figure out how to implement it on a quantum computer, that is going to have a cost that is linear in the number of gates, not linear gates in the number of elements. And there are other models such as based on sparse oracles and all that, but in the setting where we have n units of arbitrary data, all those take at least n gates. So no exponential speedup in the strictest fault tolerance setting due to this data input problem. So what does it mean to load data? There are actually quite a few methods. Here we have n arbitrary b-bit numbers. They're given to us on a piece of paper. And in one example, say perhaps we want to implement a unitary where the elements are precisely these entries. In another example, these elements, they are the coefficient of some state, so the state encodes our data, maybe the training vector. And in yet another example, maybe you want to synthesize a data lookup oracle. So this is a Boolean function. You feed in an index x, and then it does a bitwise XOR of your output into some output register. In the fault tolerance setting, the costs that we associate with these are the number of qubits we need, the Clifford gates that we use, the number of T gates, the depth, and so on. And it's commonly assumed that T gates are the most expensive component of this. In various schemes of magic state distillation to make T gates, they have a space-time volume that I'm told is between 100 times to, say, 10,000 times of each Clifford gate. This depends very sensitively on your encoding scheme and your error rates. And also, we make a pretty big assumption here, which is that you have all-to-all connectivity at the logical level. So, what are the best results that we have for these routines in prior art? So the result that kind of started it all was a result by Solovey and Kitav. If you are given a list of numbers that specify a 2x2 unitary, how many Clifford and T gates do we need to make this thing? And it turns out that, at least for the case of fixed dimension, it is logarithmic in the error, which is great. Then, using this as a subroutine and more general approaches, if you want to simulate a bigger unitary or arbitrary states, the number of qubits that you need, well, that's just log in the number of entries you want to load, because number of qubits is log of that. Number of T gates is linear, and the number of terms you want. Number of Clifford gates is linear, number of terms you want. Number of T gates is close to linear, the number of terms you want. And these are all kind of tight, you know, we have lower bounds that match these upper bounds up to log factors. So all of these approaches to the left, unitary synthesis and state preparation, there are reductions to this scheme on the right, which is just data lookup. There's a way to do all of these using log n queries to a data lookup oracle. And if we can make improvements to the data lookup oracle, we automatically get improvements to the other problems. Maybe the other problems might not be solved as optimally as if you didn't go through this reduction, but these results have wide applicability. So when we focus on the case of the data lookup oracle, here I have in this table some of the important parameters. Is it fault tolerance? The implementation, how many qubits it uses in this setting, Clifford gates, T gates, and so on. So the original vision of QRAM was by Giovanni, Seth Lloyd, and Mosca. And in this setting, it is not fault tolerant, so let's not consider that. Let's look at an implementation of it that is fault tolerance. So this was work that was done in 2015. And then they found out that if you insist on having a fault-tolerant implementation of this data lookup oracle that kind of mimics how QRAM behaves, you get these parameters: linear scaling with respect to the number of terms for qubits, Clifford gates, T gates, and the depth is great, it's log n. However, you know, this is a huge number of qubits. And you know, we would like to bring this down because our hardware is always going to be limited. We don't have infinite qubits. So an alternate approach, this is called QROM, it's by the Google group. Here, instead of having many qubits, let's kind of just sequentially apply the terms. So now you only have a log number of qubits in the number of terms, and if the output are b-bit numbers, then you use b additional qubits to store the output. And so the scaling is basically the same except for Clifford gates. It's a factor of b times bigger, and the depth is worse because you're doing things sequentially. So this scaling essentially constrains the performance of all of these algorithms where you have classical data input in. Can we make this better? Well, T-gates are the most expensive, so the most obvious question is, can we make the T-gate scaling better? Instead of linear in terms, can we make it sublinear? There are some reasons why this might be possible. We have lower bounds on the gate complexity, but this is for all gates. Maybe T-gates are special. Perhaps if you look at T-gates alone, you can have much fewer of them. Can we interpolate between these two schemes? Here, as we have more qubits, that goes down. I think it's folklore that people know that we can do this, but I haven't seen anybody do it before this paper. And can this trade-off be profitable? Because if you use more qubits, that is fewer qubits you have available to make T-gates. So if you use all of your qubits to reduce the depth, but you're making T-gates more slowly, maybe it doesn't pay off in the end. So in this work, we give affirmative answers to all of these. Yes, the T-gate scaling can be sublinear in certain conditions. Yes, you can interpolate these schemes to get the depth down, and there is a way to always make this trade-off profitable, even accounting for how qubits that you use subtract from T-gate factories that you can apply. The reason why this works is because as we use more qubits, so if we use a factor of 10 times, if we use an additive factor of 10 qubits, O10 qubits, the T-gate count decreases by a multiplicative factor of O10. So more importantly, when you use these additional qubits, these qubits in a sense they are free. They are dirty qubits. They can start in some arbitrary initial state, and at the end of the algorithm, they end in the same arbitrary initial state. So what this means is that if you use this as a subroutine in some bigger algorithm, any idle qubits that you have, you can always use it free of charge just to bring the T-gate count down, even if they store something. They just need to be idle. And what is quite remarkable is that if you were to optimize our T-gate complexity, there is a minimum at square root n T-gates. So if you want to load in n units of data, in the very best case, this is linear scaling in Clifford gates, but square root scaling for T-gates. Of course, you wouldn't always want to get the square root scaling because T-gates are only a constant factor more expensive than Clifford gates, but this can reduce. Now, if you can make your T-gate cost subdominant to the Clifford cost, then that's pretty awesome. And then all of these results, they imply similar improvements for unitary synthesis and also state preparation just by standard reductions. So how does it work? Actually, the answer for how this works is embarrassingly simple. We basically interpolate in a kind of straightforward way between QROM and QRAM, so it helps to walk through briefly how these work. So here on the top, I have a circuit showing how QROM kind of works for the case of n equals to 4 data entries. We essentially iterate through all n possible bit strings. So the first gate is thoughtfully controlled on the 0, state. If it's 0, 0, you apply an X onto that 0 register, and then controlled on this, you apply an X gate, a controlled X gate, where this is classically controlled by the value of the bit you want to apply. So you iterate through all of these bit strings, and then there are ways to optimize this circuit so that if you have n of these data elements, the depth is n because there are n things to iterate through. And because the thing that writes the bits into the output is a Clifford gate, that's controlled X, it doesn't really matter how many bits of your output you have. Could be 10 bits, 100 bits. The number of Clifford gates is always bits times depth, but the number of T-gates stays unchanged. Then here at the bottom, I have a kind of QRAM. It's not exactly QRAM, but it does the same thing. Instead of writing all of the outputs into a single register, we instead duplicate the output register some number of times, r times, and then we write the output that we want using only an X gate into each of these registers. Then controlled on our index X, we perform a number of swaps to move the register that is indexed by X to some standard output register. So in this case, a 0th register. So if you have R registers, then you have R swap gates, and each swap gate uses one Toffoli. One Toffoli can be decomposed into 4 T-gates if you don't care about phase. So that's how you get the results in those table, which is the same as the earlier slide. Essentially, the number of T-gates that you need is linear in the number of elements, and for the swap network, it's also linear in the number of bits. So now we just mash these two components together. We have our index X. Let's split it up into 2 parts. There is the quotient and the remainder. We will use the quotient to control the select, and we will use the remainder to control the swap network. The select, instead of writing in 1 bit string at a time, will now write R copies, or rather R bit strings at a time. And we can write as many bit strings at a time as we want while only paying more Clifford gates, because the indexing, the control and indexing is determined only by T-gates, but the writing of the data is determined only by Clifford gates. So now here we have a case where the select circuit is of the same depth as before, that's 4, and the swap network swaps the same number of registers as before, that's 4. But all of a sudden, we can index 4 times 4 elements, that's 16 elements. And so if you express the number of the cost in terms of the number of elements you want to load and the number of times you replicate the output register, you suddenly find out that because of this kind of meet in the middle algorithm, the T-gate count goes down multiplicatively as you increase the number of copies of your register. There is a limit to this. As you have more than square root n copies, your T-gate count goes up, but we provide an alternate construction where it still remains at square root n while having letting the depth go all the way down to logarithmic. So this is great. We can do data lookup with very few T-gates, and in an extreme limit, you could just imagine that the T-gate count is negligible compared to the Clifford count. Whether this is useful in every single situation depends a lot on your actual device. You have finite number of qubits and all that. So here, in those previous constructions, we looked at the case of clean qubits, but we can extend this to dirty qubits pretty easily. The key idea here is that when we write our bit strings into the output register, these are linear functions. You're just doing a bitwise XOR. So you can use a certain toggling trick that was in a paper by previous interns at Microsoft, the toggling trick. And this allows us to obtain the output even if all the additional qubits that you use are in arbitrary quantum states, because you're only looking at the difference between two different operators. The proof is on the right, but I think it's straightforward enough if you want to look at the paper. So the short message is that it doesn't matter what state your additional qubits you use are. They start in any state you want, they end in the same state, and they somehow catalyze this circuit. They make the T count smaller even though they don't really do anything. So is this optimal? It turns out that yes, we can prove that this is optimal in certain regimes. The most interesting regime is where you don't have too many qubits. So in this case, where the number of qubits is at most square root of the number of terms. That's also where we get the smallest T-gate count. In this regime, we can prove this lower bound on the number of T-gates you use. And what's interesting is that this lower bound is a parameter of the number of terms and also the number of qubits you use. So it is something that captures the full complexity of the select swap network. And what this means is that you can't really expect any improvement for writing data writing data into a quantum algorithm. This is the best you can get if you assume you always have a finite number of qubits. And the proof is quite simple. This is just based on the counting argument. If you have a Boolean function with n input indexed by x, and then the output is b bits, there are only 2 to the b to the n Boolean functions, then you can now count how many distinct quantum circuits there are that act on BR qubits and use MT gates. So if you multiply all of these factors together and compare them, that's how you get your lower bound. And the reason why it's restricted to being being correct in the regime where you have fewer than square root n copies of your qubits is because of the Clifford gate factor there, where you have BR squared Clifford gates. That's just math. So now that we have this data lookup oracle, applying it to state preparation and unitary synthesis is not too difficult. We already have a lot of ways to do these things. For instance, there's a method by Shende Bullock and Markov where they decompose preparing arbitrary state in terms of these boxes here. These boxes, they are called multiplexed single qubit rotation. What they mean is that if you feed in some index state, they will apply some arbitrary rotation where this rotation is predetermined. So you can simulate these multiplexes using your data lookup by a fairly straightforward sequence of transformations. First, you write your desired angle into the output, then you apply a rotation controlled by each output bit, and then you uncompute. And if you do additional math about what's the best way you could do all of these controlled rotations, it turns out that the bits of precision you need is pretty good. It's log into the error, so that's good enough for us. And then now we can also look at whether we can prove lower bounds on what's the absolute best way you could prepare any quantum state in terms of T-gates. So by applying some results by Beveland, Campbell, Howard, and Kluchnikov, there's a theorem there which can modify, and it gives this lower bound on the number of T-gates you need to make any quantum state, even assuming that you have the power to post-select your Pauli measurements. And that's quadratic in the number of T-gates. And with our approach, you can get square root scaling in the number of T-gates. So that's tight, up to log factors due to the scaling with respect to error. So we now have a way that works in principle to give you pretty good scaling in respect to T-gates. How well does it work in practice? So if you feed in the constant factors, it turns out that actually it's pretty good. QROM is considered state of art, and it's a really low overhead way to implement a data lookup oracle. And all of our select swap approaches, these alternate approaches that use 30 qubits, the constant factors are at most like factor of 2, bigger than the T-gate count. And if you were to say make a comparison with Shende Bullock Markov for preparing arbitrary states in this graph, you can see that, so if you want to load in 100 million elements, then you get some non-trivial speed up if you use enough qubits. But I must iterate that we don't always have that many qubits available, and there will always be a point where maybe this trade-off doesn't fit. Still, moral of the story is that data lookup oracles, they are very common in a lot of algorithms where you have classical data in and classical data out. And in these algorithms, in a lot of cases, they are high depth, so the data lookup must be fault tolerant because you are querying the box. The unitary is queried forward and also in reverse. And we can abstract the cost of data lookup in terms of the number of T-gates plus the number of Clifford gates, where T-gates are some large factor bigger in cost than T-gates. So by using a tunable number of R dirty qubits, we bring the T-gate down by a multiplicative factor of R, and the depth also goes down. So this is great. It gives you a speed up in sessionality for free because any algorithm that you run might not fill up your whole quantum computer. Are those qubits useless? In this case, they are not. You can always use them to decrease your T count even if they are clean. They don't have to be dirty, they just have to be available. And so that's it. Now I have to insert this slide about checking out our Quantum Development Kit. Thank you.
Okay, we have time for some questions. Everybody's really shy about questions this year. Someone in the back.
Yeah, actually, so Guang Hao, on your T-gate count as a function of the number of dirty qubits, I just didn't quite follow, what defines the minimum there, and why is it?
Right. So if you were to look at the T-gate cost of, say, any of these select swaps, the scaling is number of terms over R plus R. So if you increase the number of dirty qubits, the T-gate count first goes down. Then at least for the select swap scheme, it then starts to go up again. But we have another construction where it stays down, but this was the simplest one to explain.
Yeah, so I guess, can you say a little bit about what, obviously you would just quit putting in dirty qubits.
Yeah, you could always do that.
But why does adding more really, why does it have to hurt you? It's just the
For
construction.
this implementation of the data lookup oracle, it hurts you in T counts. But we have another implementation that doesn't hurt you. As you add more qubits, the T count still stays at the square root n factor. However, the depth continues to go down. That's the reason why we might want to use more qubits, because depth goes down. And assuming you have infinite qubits, lower depth means lower execution time. In QRAM models, you assume log depth, so you can always get your exponential speedups, but you ignore how each of these queries have linear costs.
Okay, thank you.
More questions? I have a question. So the depth is still scaling like capital N, right? What was the depth again?
So let's go to one of the earlier slides. Right. So the T depth, this goes down monotonically as you increase the number of dirty qubits all the way down to log squared R depth. And then if you look at the Clifford depth as well, there's a way to parallelize out the Clifford gate so that you also get your monotonic decrease in depth. Although Clifford depth is more of a special case matter because it depends a lot on how you do your Clifford case in your your error correcting code. Sometimes there are all sorts of ways.
Okay. Other questions? Okay, if not, let's thank Guang Hao again.